on the screen. Welcome everybody. This is a virtual colloquium. I don't remember which one number, but I'm glad to see so many people joining today. Today, I'm very happy because Rafael is going to talk about the multi-messenger view of the ultra-high energy universe, which is a very interesting topic for me. Before starting the seminar, I would like to say a few words about Rafael. Rafael has graduated from the University of Hamburg in Germany in 2015, and since then he has been traveling quite a lot over the world as a postdoctoral fellow. So in 2017, he also, in 2017, he became, 2015 to 2017, he was a postdoctoral researcher at the University of Oxford in the UK. Then he moved back to his country, which the country of residence, let's say Brazil, 2017, and for 2 years. And then he returned back to Europe as a Radboud Excellence Fellow, which is a prestigious fellowship given by the Radboud University in the Netherlands. And most recently now, he is also a La Caixa Junior Leader, which is a group leader position in the University of Madrid in Spain, and also holds a position, a Marie Curie Fellowship at the Institute of the Theoretical Physics of the same university. Marie Curie Fellowships are very competitive, so it's a great honor, I suppose, for Rafael to be awarded this, this fellowship. And Rafael has many research interests. He's mostly known for his work on cosmic rays and cosmic ray propagation. He is one of the developers of the public propagation code for cosmic rays, which is known as CR-Propa. But he has also worked on many other things. He has worked on the generation of cosmic magnetic fields, how these are formed and how they evolve across the universe. And he also has also worked on basic physics. Let's say he studied, he worked on astrophysical and cosmological probes of the Standard Model for physics. And he most recently started working also on dark matter, and he moved into the gamma ray regime, as I learned recently. Rafael has also done, he has also some teaching done, and he has also done a lot of outreach on the same topic. And we are very glad to having you here, Rafael, and the floor is yours now. Thank you very much for accepting our invitation.
Okay, so thank you very much, and thank you very much for the invitation. Hopefully in another opportunity that I can come in person to Athens, never been there, to give a colloquium in person in the future. So after this very nice introduction, I'm going to talk now about a multi-messenger view of the ultra-high energy universe. So what I'm going to do here is to combine many apparently different things, but I'm trying to make the case that they are all connected, the different messengers, in terms of how they are generated and what they can teach us about the universe, as you'll see. Okay, so essentially, this is an overview of what I'm going to talk about today. We have at the top here cosmic particles. We have on the left fundamental physics, on the right cosmology, and the bottom cosmic accelerators. So if we want to learn how these cosmic particles of high energy and ultra high energy, they are produced, well, we need to have two ingredients. We need to know like details of the cosmology and of the fundamental physics, like how particles interact when they are traveling, things that happen in the universe, distributions of magnetic field, the expansion of the universe. And you know, the arrow in this direction, it gives us information about cosmic accelerators. Similarly, we could also use these particles to try to learn something about fundamental physics. And when I say fundamental physics, I'm referring to things like particle interactions, the kinematics, or maybe some process beyond the standard model of particle physics, like signatures of quantum gravity, that might leave a signature in these high energy cosmic messengers that I'm talking about. So if we know information about these messengers. We know where they come from, so we know the cosmic accelerators, and we know the details of cosmology. We can answer some questions about fundamental physics. In a very similar way, we can also do some cosmology by assuming knowledge of cosmic accelerators, using these different cosmic particles, and having knowledge of fundamental physics. So it's the arrow in the other direction. Okay, can you see my pointer? Sorry, you cannot, right? I'm pointing blank here.
No.
Okay. Well, I'll just say things, yeah. Sorry, it's not showing up anymore.
No problem.
So moving on, this that we are seeing here, it's the spectrum of different types of particles like cosmic rays. There are also some electrons, gamma rays here, neutrinos, as you can see. And you can see that this spectrum, the energy spectrum, it covers many orders of magnitude from 1 GeV up to 10 to the 12 GeV. So that's like 11 orders of magnitude in energy, which is huge. And in the vertical axis, you can see the flux of these particles in units of energy per area per solid angle per time. And this variation in the vertical scale tells us that the flux of these particles also change a lot. And at the very high energies, we have very few particles compared to the very low energies here, shown in this figure. And what I'm going to talk about today are mostly the cosmic rays shown here in this orange circle, with these energies above 10 to the 15, 10 to the 16 electron volts. I'm also interested in these neutrinos observed but mostly by the Ice-Cube Neutrino Observatory with energies around 1 PeV, and also the gamma rays with energies around TeV, which is relatively high for gamma ray standards. And these messengers, they are usually detected through a variety of different techniques, right? So the way this usually happens is that they cause a shower in the atmosphere, and what we actually measure at these high energies for the messengers that I mentioned, that I'm talking about, what we actually measure are the showers they develop in the atmosphere. So let's suppose we have a cosmic ray. As the cosmic ray impinges upon the top of the atmosphere, it causes a shower of particles, including like several pions, kaons, mesons, protons, neutrons, whatever. And these interactions emit some fluorescence light that can be observed with what we call fluorescence detectors that are on the surface of the Earth. Similarly, we could also have some satellite in space looking down to Earth on the atmosphere, looking at this fluorescence light emitted by these first interactions of the cosmic rays. And as the cosmic ray continues to develop, they can reach these so-called particle detectors, which are, for example, water Cherenkov tanks. These are just huge tanks with pure water, dark, with photomultiplier sensors inside of them. And by collecting all these particles and all these different particles and assuming that we know how they interact in the atmosphere, we can just reconstruct the properties of the cosmic ray that impinged upon the atmosphere. And of course, during this process, we can also have emission of radiation, in this case, in radio frequencies with hundreds of gigahertz that can be detected with radio antennas on the surface. Well, we can also have gamma rays, and gamma rays, when they interact with the atmosphere, they also cause particle showers that emit Cherenkov light that can be seen by Cherenkov telescopes here on the ground level. And these are the most common techniques to detect different types of messengers of high energies reaching the atmosphere. And one of the things that I would like to talk about today is related to this plot. This plot, you'll see it many times today. It's a thematic plot. I'll come back to it every once in a while. And it shows the fluxes in gray measured by different cosmic ray experiments like the Pierre Rogier Observatory. It's in gray on the right side. It also shows measurements of the diffuse gamma ray background as observed by Fermi. It's shown on blue on the left side. And the orange markers show the measurements of the diffuse neutrino flux measured by the Ice-Cube Neutrino Observatory. And if we draw a horizontal line in this plot, more or less connecting the high energy part of what we see in gamma rays with the neutrinos and with the cosmic rays, we see that these fluxes, they are comparable. And if they are comparable, we can ask ourselves, okay, a reasonable hypothesis is that they might have a common origin. I'm not sure, but we can entertain this hypothesis and say, okay, if they have a common origin, so if somehow the flux of cosmic rays, the flux of neutrinos, and the flux of gamma rays is connected in some way, if they have this common origin, this connection can be established either in the source, in the astrophysical source that produce these messengers, or somehow during their journey to Earth, right? So there can be production in the source or during propagation. And that's the thing that we need to understand. We need to understand how these messengers are produced in the source and how they travel from their source to Earth. And to do that, we'll make this connection now. Most of the particles that I'm going to talk about today, of course, there are others, but the most important ones are these: cosmic rays, electrons, photons, and neutrinos. And one of the questions that we would like to answer here is, how are these particles produced? How can they reach such very high energies that we observe? Because we observe cosmic rays, for example, with energies of 10 to the 18 electron volts, even 10 to the 20 electron volts, which is like 10,000 times larger than what the LHC can reach in terms of energy. So these energies are huge. So how are these particles produced? In the case of charged particles like cosmic rays and electrons, they are usually produced via some kind of astrophysical electromagnetic process that requires an astrophysical object with a magnetic field, and this astrophysical object has a given typical size. That's what's shown here in this plot. What you are seeing here, it's the so-called Hillas diagram, in which the vertical axis shows the strength of the magnetic field in a given region, in a given astrophysical environment or object, and in the horizontal axis, you are seeing the size of this object. And essentially, the Hillas diagram is showing us what are the astrophysical objects that are capable of accelerating charged particles, either cosmic rays or electrons, to high energies. And this is essentially a competition between some kind of astrophysical acceleration mechanism taking place inside this object and the magnetic field in this object, because the particles are charged, they are confined within this region of the object, right? And as they are accelerated, at some points, they will have so much energy that they will no longer be trapped inside that environment because their energy is too high, and they will just, leave this object. So this is what this plot and the so-called Hillas criterion is showing. If we are talking about neutral particles, how do we get neutral particles with very or ultra high energies, like photons and neutrinos? Well, this is usually achieved through some kind of interaction process, like cosmic rays and electrons can interact with gas or with radiation, like photons present somewhere in the universe, in the vicinities of an astrophysical object, producing the photons and neutrinos that we observe here at Earth. So every time I refer to like photon neutrinos or photons or neutrinos from the source, I'm talking about some of these processes in which these particles are produced within the object. And another important thing is, every time I talk about ultra high energy things, I'm referring to, broadly speaking, the science case of everything that is generated by particles with energies above 1 eV. 1 eV, for those of you who are not familiar with this unit, it's 10 to the 18 electron volts. So if we have a cosmic ray with 10 to the 18 electron volt that produces like a gamma ray with 1 GeV, that's part of the ultra high energy case that I'm trying to make here today, okay? So moving on, the multi-messenger picture also requires two components if we are trying to connect these different messengers. I just talked about how they are produced in astrophysical sources, and now just to get a better idea, here in red, it's shown the cosmic rays in an astrophysical object. They can interact, producing the neutrinos, or they can produce gamma rays, which can then produce electrons, which can produce more gamma rays, and so on. There can also be emission of gravitational waves. And that's the multi-messenger paradigm, by combining all these messengers from a single source. But these processes, they might also happen during the propagation after these messengers leave the source. In the case of cosmic rays, they just, leave the source, they are emitted by a source, they travel in the universe, but the road's very bumpy for them because there are magnetic fields and cosmic rays are charged particles, so they are continuously being deflected by these magnetic fields outside the galaxy and in our own galaxy. During their propagation, they can also interact with like photons that are present in the universe. For example, the cosmic microwave background, the CMB. The CMB is a target for these cosmic ray interactions. And they can produce other cosmic rays out of a primary cosmic ray. And they can also produce neutrinos, or they can produce photons. So these interactions produce a bunch of other particles that we can actually detect here at Earth. These particles produced during propagation, I'll refer to them as cosmogenic particles. And in the case of gamma rays, how do they propagate? Well, gamma rays, they usually propagate for a given distance if they have very high energies, right? But the universe is opaque to their propagation. So the high energy gamma ray can interact with photons, for example, like the extragalactic background light or the cosmic microwave background, producing electron-positron pairs, which are then deflected by magnetic fields along the way, if there are magnetic fields, and then they will bump into more photons, producing more high energy photons. And this process can happen many times. This is what we call an electromagnetic cascade. Okay, this is how gamma rays propagate in the universe. So every time we look at a gamma ray here at Earth, we cannot be 100% sure that it's a primary particle that left a source. It can be actually just the byproduct of all those interactions that I shown you before. In the case of neutrinos, well, there are magnetic fields in the universe, this type of things, but neutrinos, they just travel unimpeded, essentially, like they essentially don't interact at all. Their interaction rate is very low. So they are very good messengers because they can probe the universe to very high distances. They just travel without interacting with anything. And the universe has many photon backgrounds, as I mentioned before. There is like the CMB, and there is other backgrounds like in infrared, in radio, and so on. And, several of these backgrounds are shown here in this plot, like the cosmic radio background, the cosmic microwave background, the extragalactic background light, which is essentially infrared and optical radiation. And all these photons, they are present, they pervade the whole universe, and they act as targets for whatever particle is traveling in the universe, whether they are cosmic rays, whether they are gamma rays, and so on. And as I mentioned, there are also magnetic fields in the universe, like intergalactic magnetic fields. And what I'm showing here in this video, it's the distribution, it's the so-called cosmic web. This cosmic web, in green, you can see clusters of galaxies. They are connected to each other through these filamentary structures that we call, well, filaments. And the black regions are essentially like the center of the black regions are cosmic voids, which are just empty regions without the structures, right? The magnetic fields in the universe, they follow more or less the distribution of these structures. And if we just plot the cumulative distribution of the magnetic field, actually 1 minus the cumulative distribution, that's why it's falling down in this figure. For the different regions, we see that we really don't know a lot about these magnetic fields. Each one of these lines that we are seeing are a different model for the intergalactic magnetic field distribution in the universe, like including clusters, filaments, cosmic voids. But what we do know is that cosmic voids, they fill most of the volume of the universe, right? Because as you can see in the video, most of the image is black. So intuitively, we know that it fills at least like 10 or 20 or even 50 or more % of the volume of the universe. And therefore, cosmic voids, they in principle should be the dominant source for most particles that are traveling in the universe, like ultra-high energy cosmic rays. Okay, keep that in mind because now, very soon, we'll start to bring all this information together. And I've already introduced how these messengers are produced. I've discussed now how they travel, the interactions they undergo, and this type of things. And why do we need to know that? Well, we need to know that because we want to describe the things that we observe to better understand nature. And to do that, we need to build models. And in order to build models, well, for this type of things, we need to start with some kind of astrophysical inputs. When I say an astrophysical input to build a model, we need to know like which type of astrophysical object we are talking about, more or less. So we need to know that a given type of astrophysical object is emitting particles, whatever type of particle you want, like gamma rays, cosmic rays, neutrinos, with a given spectrum, so a given energy dependence. In the case of cosmic rays, we also need to know the composition. So if it's a helium, if it's an iron nucleus, and so on, we need to know how many sources of this type exist in the given model. So we need to place them somewhere in the universe and tell their time dependence, so how they evolve with the history of the universe. And once we have established these initial ingredients that we need to put together regarding the source, we just input them into some kind of propagation model. The propagation model essentially tells us what happens when this messenger produced by the astrophysical source, considering these astrophysical inputs, travel in the universe. Do they interact with those photons? Do they interact with the magnetic fields in between? And these type of things. That's what the propagation model gives us. And after that, well, these particles, they will just travel from their source through the universe, interacting with stuff until they reach Earth. That's how we build a model to compare with observations, right? And if you're building a model, well, we want to get the energy distribution of these particles, so essentially the spectrum. In the case of cosmic rays, we need to know the composition. If you're talking about the neutrinos, we need to know the flavor of these neutrinos, the arrival directions, so which direction from the sky they come from, and when are they arriving, at which time, right? And that's what we effectively compare with observations. And now that I've put all these ingredients together, we can actually do something more concrete, like more phenomenological. We can compare models that we come up with, things that we can invent. That's how we test it. We test the models by comparing with these observations. And to do that, to build these models, before I actually go to this part, sorry, to build these models, we actually need some kind of computational tools, right, to interpret the observations. And these computational tools ideally should treat all messengers in a very consistent way and scan the whole parameter space of uncertainties that we have regarding all these ingredients of the model. Therefore, we need some kind of multi-messenger framework that combines all the messengers and all these ingredients within a single computational framework that can just, we give the inputs, it just spits out the output that we want. And that's what this CRPropa code does. CRPropa is a publicly available Monte Carlo code. You can check it out on GitHub. It's parallelized. You can propagate cosmic rays, gamma rays, neutrinos, electrons in any astrophysical environment that you want, as long as it's at high energies. It's very modular, so there are different types of interactions for each type of particle. And, if you just want to use it to do, like, for people working with physics beyond the standard model, they have some kind of new particle, they can just create a module and plug their new particle in here, in these blobs that you're seeing. So it's very modular, very easy to be extended. So it's a very powerful framework that's been now used for ultra-high energy cosmic ray studies and also gamma ray studies and neutrinos. Among the applications of CRPropa, what you can see is that like here, just, I'm shamelessly advertising a code that I worked on the development. So, I'll just be quick here, but you can do many things, including studying cosmic ray models, try to interpret the observations. You can compute fluxes of cosmogenic neutrinos. You can study how neutrinos are produced within galaxy clusters. You can constrain magnetic fields in the universe using like gamma rays and cosmic rays, using CRPropa simulations, and so on. Okay, now how do we make sense of the observations using, for example, a framework like CRPropa, which brings together all those ingredients that I was talking about? Well, to make sense of observations, we first need to know what's interesting about each one of these messengers that we have. So each one of these messengers here, like cosmic rays, photons, and neutrinos, they have some strengths and some weaknesses. And there are many open questions related to one, things that are not answered in one of the messengers that the other messenger might help answer. In the case of cosmic rays, we don't know a lot. We don't know how they are produced. We don't know how they can get to these high energies exactly, and so on. In the case of photons, we don't exactly know all the details of how they are produced, and so on. And in the case of the neutrinos, there are also some open questions. And but all these messengers, they are very useful to do things like dark matter studies, to probe the distribution of photons in the universe that I was just mentioning. They can also be used to study cosmic magnetism and fundamental physics. So as I was saying, each one of these messengers has an advantage and a disadvantage. And the advantage, for example, of ultra-energy cosmic rays is that they are relatively easy to detect, but we cannot see very far with them because they interact during propagation. And they are affected by magnetic fields, which makes it tough, you know, to do some kind of real astrophysics with them, at least directly. Photons, on the other hand, they are also easy to detect, and we can see relatively far depending on the energy. And neutrinos, we can see as far as we want, and they travel, you know, they don't interact with magnetic fields, so they are very useful, but they are hard to detect. And now let's go back to the plot that I've shown you before, this thematic plot. I asked first, if we draw a horizontal line connecting the different messengers, like the markers, the blue, the orange, and the gray markers, do they have a common origin or not? Well, if they have a common origin, one possibility is that they are connected to some kind of cosmogenic process, meaning that the ultra high energy cosmic rays shown here in the circle in red, they can be responsible for the gamma rays and the neutrinos that are shown at the lower energies here, right? Is this connection true? Well, to know that, we first need to collect ultra high energy cosmic ray data. This is what the Pierre Roget Observatory has done. So what we are seeing on the right-hand side is just the flux of cosmic rays observed by the Pierre Roget Observatory, right, at the high energies. And what we are seeing on the left side is the so-called Xmax, which is essentially the composition of the ultra high energy cosmic rays. So you can see the red lines are protons, the blue lines are iron nuclei, and the observatory measures something in between these two. So as we go higher in energy, the composition becomes increasingly heavier. That's what we can tell about cosmic rays. And using these observations to answer the question whether the cosmic rays are connected to the neutrinos and the photons, we can just try to fit this. And to fit this, well, we can come up with some kind of astrophysical model which contains all the ingredients that we're interested in. This astrophysical model essentially says that, you know, the cosmic rays are accelerated by some kind of power law with an exponential cutoff around Rmax. Rmax is essentially like a proxy for the maximum energy to which a given astrophysical source can accelerate cosmic rays. And then we can try to fit the ultra high energy cosmic rays observations, you know, considering different values of alpha, which is the spectral index, or Rmax, and the cosmological emissivity of the sources. And, you know, by playing with all these different parameters, we can try to see where our best fit lies and try to learn something about the sources of ultra high energy cosmic rays, as shown in these lower red yellowish plots. And once we have done this fit, we can actually say, okay, now that I have these cosmic rays and I know what's my best fit, I know that these different interaction processes that are shown here, they can produce photons and neutrinos. Well, I fitted the ultra high energy cosmic ray observations. I have a model for the sources of ultra high energy cosmic rays. And if I have the model for the sources and I know how the cosmic rays interact during their journey, I can compute the cosmogenic photons and neutrinos. So these fluxes that are produced by cosmic rays during propagation. And that's what's shown here. What's shown here in this figure is essentially the flux of cosmogenic neutrinos that is compatible with ultra high energy cosmic ray data. You can see that these dashed lines, they are just planned experiments for the future, and it's very tough to detect these cosmogenic neutrinos, but you always have to keep in mind that we have assumed a given model for the ultra high energy cosmic rays. This model might not be right, we just assumed it. It makes sense, it's reasonable, but it's an assumption, right? And this is the flux of cosmogenic neutrinos that we get. It's relatively low. It cannot explain that those three messengers, you know, the plots that I had before, because this flux is very low, it's not even at the right energy. Then we can do the same thing for photons. So the only thing that changes is this plot. And what we are seeing here, it's the distribution of cosmogenic photons comparable with ultra high energy cosmic ray measurements, like the 90% confidence level, for example, it's shown in purple here. In this case, well, ultra high energy cosmic rays, they might indeed be able to explain at least part of this gamma ray flux that we see, the diffuse gamma ray flux from this plot. Well, and I started by asking, is there a cosmogenic connection? It's not very clear. Apparently, it's very hard actually to explain the neutrinos. So apparently, no, we cannot explain everything only with cosmogenic particles. It doesn't mean that it's not there, okay? And then we can ask ourselves, is there a source connection? So are these three messengers produced by the same population of sources? And just to discuss that, let's take as an example, galaxy clusters. We know there are galaxy clusters all over the universe. And what we are seeing here in this plot is the color scales indicate the magnetic field strength. This is a single cluster of galaxies, right? In a given arbitrary unit system. And at the center, I injected three cosmic rays, just you know, so to get an idea of what happens with energies of 1 eV. That's 10 to the 18 electron volts. And you just, you know, I injected this into my simulation code, CRPropa, and I just let it travel around. And you can see that the lines, you know, these are the lines. And if we go down in energy a little bit, you see that the lines, it becomes more contained inside the cluster environment. And the longer the cosmic ray is contained inside the cluster, the higher the chance that it will interact with the stuff in the cluster, like the gas. And the higher the chance that one of these interactions might produce neutrinos or photons, right? And in this work here, that was done by my PhD student, Saqib Hussain, we studied the production of neutrinos and photons from the whole population of galaxy clusters in the universe. And this is what we get. So in this plot, what we're seeing is the red circles is showing the diffuse gamma ray background, so essentially photons. And what we are seeing is that the green squares are showing the limits observed by the IceCube Neutrino Observatory, and the bands are showing our results for different assumptions. What we see is that actually galaxy clusters surprisingly can explain a significant fraction of these two measurements. So if we start with cosmic rays inside the galaxy cluster, we can make a connection between the neutrinos and the photons that we see in that plot. So now the picture is emerging. It's becoming more clear that there might actually be something interesting going on. And the original hypothesis that the cosmic rays might be producing somehow, either in the source or during the propagation, these neutrinos and photons, this hypothesis is becoming stronger. Okay, that's good news. This is a possibility. But so far, you know, when I show you this plot is essentially the diffuse all-sky flux of all these messengers. It's the integrated contribution of everything. To really answer this question now, we need to understand, to distinguish between the source and the cosmogenic possibilities, we need to understand what's going on with individual sources. So instead of looking at all types of sources in the universe, we can look at individual ones. And let's take a look at this object here, PXS0506 plus 056. You know, it's a long name, but this is a very famous object. This is a blazar that was possibly the first high energy neutrino source ever identified. And it was observed also in gamma rays and actually along the whole electromagnetic spectrum. So at the same time, neutrinos of high energies, like hundreds of TeV, were observed with electromagnetic radiation across the whole spectrum from this object, which is a blazar. And one question that we might ask is, okay, to make sense of, the framework that I've been working with, that there might be some kind of ultra high energy process going on inside this object. We need to know whether there are some kind of ultra high energy neutrinos being produced. So we can just, ice cube detect PV neutrinos, but are there neutrinos of even high energies? Apparently not. What we are seeing in this lower left plot are the limits, like the red ribbon at the top, are the limits, the upper limits by the Pierre-Roger Observatory. And, the flux of neutrinos, if we just extrapolate the ice cube measurements of these neutrinos, that's the upper limits that we get. So there are no ultra high energy neutrinos from this source, at least not within the limits that we can detect, which is disfavoring this type of object as a possible, in principle, source of ultra high energy cosmic rays in connection with the other messengers. And this one now, let's take a look at another object. This object, sorry. It's a gamma ray burst. It's GRB 221009A. This gamma ray burst, it was observed last year, hence the name 2210, so October 9th last year. And it's the brightest ever observed gamma ray burst that we saw in our lifetime, right? And this gamma ray burst, interestingly, emitted some photons with energy so high that we should not actually be seeing those photons. There were some photons from this gamma ray burst with energies of 18 TeV. And if you recall this picture that I've shown you before, all this process happened during propagation, right? You have pair production. So photons are traveling, they produce electron-positron pairs, then there is inverse Compton scattering, and so on. And this GRB, it's located at a redshift of 0.15, which is a distance of about 600 something megaparsec. And if we take a look at the typical mean-free path for the process of pair production, gamma-gamma pair production, this is shown in this upper left plot. If we take a look at an object at a distance of 650 megaparsec and an energy of 18 TeV, we don't really expect to see a lot of photons at these energies from an object at this distance, because pair production essentially kills off most of the high energy photons coming from this type of objects. Therefore, what's going on here? Well, when this happened, many people, if you look on arXiv the day after, the week after, everybody was talking about some new mechanism to explain why photons with so high energy were observed from this gamma ray burst. They were saying like, there are axion-like particles and other things like some kind of heavy neutral leptons that, the gamma rays convert into and then back from to evade this pair production threshold. Many exotic ideas were being suggested for this object, but let's apply the same framework that we've been talking about to this object. If this object is actually a gamma ray burst, is an actual source of ultra high energy cosmic rays, and it emitted ultra high energy cosmic rays towards Earth, it's a very bright event, we can use everything that we just discussed now to just estimate what's the flux of photons that we expect from this object, and what's the flux of neutrinos that we expect from this gamma ray burst. And the only assumption that we have to make is that, let's just see if this GRB, it's an ultra high energy cosmic ray source, what do we get? And then that's what I did recently in this work. The observatory that saw those 18 TeV photons, it's called LASSO. LASSO is expected to see things according to this grayish line shown in the plot. That's the sensitivity level of LASSO. And the red and orange lines here are different ultra high energy cosmic ray models that I used. And if you just make different assumptions for the ultra high energy cosmic rays from this GRB, and you let these ultra high energy cosmic rays propagate in the universe, and the photons that they produce, we just collect them and we plot it. That's what we get with this red and the orange lines. And we can see that the 18 TeV photons observed by LASSO, it can be easily explained by simply assuming that ultra-high-energy, this gamma ray burst is an actual source of ultra-high-energy cosmic rays. And as I mentioned in the beginning, we don't even know where these ultra-high-energy cosmic rays are produced. We don't know what are their sources. So this might be an interesting indication that this GRB, or gamma ray bursts, more generally speaking, might be ultra-high-energy cosmic ray sources. Just to explain a little bit more, what we're seeing here in green, it's essentially the effect of pair production that I mentioned in the previous slide, right? So a photon from this gamma ray burst, if this gamma ray burst just emits photons directly, they should be absorbed, and they should not reach 18 TeV, as you can see with this green band. But once again, the hypothesis that this object is emitting ultra-high energy cosmic rays can produce a high enough flux of photons to explain the observations by LASSO. And this happens because along the way, each one of the plots I'm going to pass along them on the right-hand side now shows the energy of the primary cosmic ray as a function of the energy of, for example, an electron produced along the way. You can do the same for photons, but the electrons, they also produce photons. So this is all connected, okay? The bottom line here is the following. The horizontal axis is the energy of the primary cosmic rays. The vertical axis, the energy, in this case, of the electrons. And the color scale tells us how much of the total energy this particle is taking with respect to the cosmic ray. And we start at the position of this GRB. As we get closer to Earth, there are fewer particles, but there are still other particles being produced. Look, you know, it's not all black like in this case, or it's not darker. It starts to become more yellow, purplish. But this is telling us that there are still these cosmogenic particles being produced along the way from the source to Earth, and therefore it's reasonable to expect some of them to arrive here. So this is a very natural explanation. And you can also do the same thing, but instead of photons with neutrinos, but in this case, the flux of neutrinos, it's not in the energy range that IceCube can observe. And yeah, so far there are no limits by observatories of neutrinos at high energies. That's what's shown in this lower left plot. Okay, in the future, I'm moving on to my final couple of slides already. So I mentioned many different types of observatories in all different messengers, and I tried to make the case that these messengers might be connected somehow. The state of the art today for ultra-high energy cosmic ray observatories is this Auger observatory shown here on the left. I'm sorry, my pointer is not working here. You cannot see it. But yeah, you can see on the left side, the Auger Observatory and Auger Prime. They are the largest facilities operating today. But in the future, there are plans to build even more sensitive facilities that will operate, you know, in 2040, 20 years from now, more or less, that might increase the total exposure of the observatory, therefore the number of particles that we can collect by a factor 10 at least, which is very good news if we want to study ultra-high energy cosmic rays. And there are also other experiments that propose to study like neutrinos and photons at high energies. The ones that I'm involved with are just RAND and GCOS. GCOS is the Global Cosmic Ray Observatory. So far, it's just a proposal to have like a large observatory that can collect all the messengers at the highest energies above 10 to the 18 electron volts, not only cosmic rays, okay? Whatever particle above 10 to the 18 electron volts that produces a shower in the atmosphere. And GRAND, which is the giant radio array for neutrino detection that I'm just briefly going to present now. The science case of GRAND is essentially to do like astronomy with neutrinos, so giant radio array for neutrino detection. It's an array in radio to detect neutrinos, but it can detect all types of particles that comes from that are produced via air showers in the atmosphere, including cosmic rays, including photons. So this is a very nice observatory. It's still, you know, it's still a concept right now, but I think this is the future for this field, because one of the points I've been trying to make today is the connection of the messengers. And I discussed like cosmic rays in the context of magnetic fields, it's hard to do astronomy, but neutrinos, they are neutral, so they just travel in a straight line. Things are better for neutrinos. Therefore, I see a future for high and ultra high energy neutrino astronomy, and GRAND might be one of the main players in the future. Okay, and the timeline for GRAND is like maybe, you know, a few decades, but the first prototypes, they are already being deployed, like 13 antennas like these. There are some being deployed now in China. That's where the first site of the observatory is going to be built. And in the future, the idea is to actually have maybe tens of arrays. Each one of them contains 10,000 of these antennas that you are seeing in the figure. I know this sounds ambitious, but it's perfectly feasible if you have like an infinite amount of money, which might be the problem. But yeah, this is actually happening right now. You know, in the past couple of months, these prototypes are being deployed. And maybe in the future, we are actually going to have an ultra high energy neutrino observatory that might complement this ultra high energy cosmic ray science case that I've been talking about so far. And let me move on to my conclusions. So yeah, this thematic plot, you've seen it many times in this talk, right? I started by asking if they are connected, these three messengers, and we saw that they might be via some kind of process happening either in the source or cosmogenic. It's not very, very clear. What's interesting, what comes out of this plot that I didn't mention before is that at the bottom, there are these bands of the cosmogenic neutrinos, right? The lower the flux of cosmogenic neutrinos, the lower the background if we are aiming to do astronomy with neutrinos, which is good. So either way, by building neutrino detectors, like by trying to do some kind of, you know, neutrino astrophysics, either way, we get something. If the cosmogenic neutrinos, they act as a background. So if their level is, they act as a background for neutrino astronomy because they are everywhere. Anyways, if this flux is low, we can more easily do astronomy. If this flux is high, we are learning about the sources of ultra energy cosmic rays. That's a win-win situation. Other interesting things is also to try to extrapolate to high energies the measurements that we have so far, like this arrow here. If we just extrapolate the diffuse gamma ray background observed by Fermi to higher energies with future facilities, what do we expect? Will this line go up eventually? Same thing for neutrinos. Will this line go up or for cosmic rays? So how far up in energy can all these fluxes of all these messengers extend? What will we learn from this in the future? We'll definitely learn something about very unique astrophysical objects that produce different messengers via very extreme and energetic processes. And I did not have time to talk about this today, unfortunately. I focus more on the astrophysical part, but as I mentioned in the beginning, we can use all these messengers alone and together to do some kind of, you know, fundamental physics, look for signatures of physics beyond the standard model, and so on. Yeah. Yeah, sorry. And yeah, in the future, you know, I mentioned throughout my talk, this is just to summarize everything, that there are some difficulties in model building. There, it's not trivial, as you've seen. We have to take into account photons, distribution, magnetic fields, distribution of cosmic ray sources and everything. So yeah, that's very challenging theoretically and computationally, and we do need to make some progress on that, on those directions if we want to move on to make sense of this, to unify this ultra high energy picture that I've been proposing here. There are also some experimental challenges by future generations of experiments, like, you know, in the future, gamma rays will be observed with unprecedented sensitivity with CTA, the Cherenkov telescope array. We also have like neutrino observatories like GRAND, observing mostly focusing on neutrino observations at the highest energies, which will complement the ultra high energy cosmic ray science case, and other observatories like GCOS, the Global Cosmic Ray Observatory, might also become a reality in the future. And yeah, that's all I had to say. Thank you.
Thank you very much, Rafael. It was a very nice talk, a very nice journey across the messengers. And I think there is time for questions. So feel free to unmute yourselves and ask Rafael if you have any questions. I see one hand raised by Apostolos Mastichiadis.
Yeah, hi. Thank you very much for your talk. I was wondering about this GRB that you mentioned. So what are the assumptions? You start producing the ultra-high energy cosmic rays. You don't have any interactions in the source, and you just propagate them. Now, what you do once you produce an electron-positron pair, for example, from gamma-gamma or from a pion, is it deflected or not? Because if you assume some magnetic field, then you lose your particles, and you produce something like what Prothero was mentioning many years ago, a halo of radiation around the object, because exactly of this diffusion of electrons. And so what are your assumptions?
Exactly. In this case, it was the one-dimensional case, so magnetic fields were not taken into account. However, because magnetic fields are not really known, intergalactic magnetic fields, in the beginning of the talk, I showed like that the volume filling factors of magnetic fields, right? And I argue that voids are the dominant contribution for the magnetic fields. Actually, I can probably show that. No, sorry, yeah. It should be, yes, it's the next one, okay. I showed this plot, and I argued that, I said that we don't really know anything about magnetic fields, and I argued that the voids, which fill most of the volume of the universe, they are the dominant contribution for whatever you are doing. In this case, I wrote total energy cosmic rays, but it's also true for the electrons. The assumption is magnetic fields are lower than 10 to the minus 14 Gauss. If they are more than 10 to the 14 Gauss, you get too long time delays. You cannot observe the photons from the GRB because we are actually seeing secondary photons, right? The electrons will be time delayed, and they will be delayed by maybe a few days or weeks or years. And everything has to be within like those time, within that time window of, I think it's 2000 seconds or maybe, order fraction of a day. Okay, so if magnetic fields are strong, larger than 10 to the minus 14 Gauss, then we cannot really do that. The hypothesis doesn't really work. But because magnetic fields are not known, it's reasonable to assume that they are weak. And in the paper that I presented there, yeah, I did all these estimates for the different strengths of magnetic field. And I argue that, if it's stronger than 10 to the minus 14, things are more difficult. But if it's less than 10 to the minus 14, which might as well be the case, then it's fine. Everything works.
Okay, thank you. And another smaller one, when you saw the clusters of galaxies and you had the cosmic rays traveling around and producing, did you take into account the X-ray fields that these objects have?
No,
it's not clear.
That's a
because
very
there
good
are
point.
lots of X-rays. So I was wondering whether calculations take this into account, because they're high energy and therefore easily to do all of your secondaries that what you want. But I'm not sure the numbers, how they come.
Yeah, exactly. This is a very good point. Actually, this is the next thing we are going to do very soon. We do not take the acceleration part into account for this, because we assume that the cosmic rays, they already gain energy through some other process. So this pre-modeling is already, it's in the assumption, and we just plug it in the simulation, because we are focusing more on the modeling of the interactions.
Okay, thank you.
Yep.
Are there any other questions? I might ask one since we are at this slide, because I also had a question about that. And give some time to the other participants to think of their questions. So one question that I had is the following, basically one comment, because you show here what are the predictions for the diffuse gamma ray flux. And there are, within this band, there are some cases, I suppose, that overshoot the gamma ray flux. And the other thing is that we currently know, or we have an understanding that at least above 100 GeV, this isotropic or the diffuse gamma ray flux background can be explained by blazars, almost 100%. So I was wondering, does this, I mean, can you use this in order to exclude some part of the parameter space? And will this actually move down your prediction for the diffuse neutrino flux?
Yes, you're completely right. So clearly there is part of the parameter space that's excluded. However, there is also some room here for, you could play, for example, with the total cosmic ray luminosity there. And if you decrease it by a factor 10, this band will go down by a factor 10. But in any case, part of the parameter space here definitely can be excluded, period. But you said also that the high energy can be explained by blazars, which is, I agree, perfectly fine. This is well known. On the other hand, this contribution, it's also kind of, you know there is gas in clusters and you know there are cosmic rays. So this contribution is in some sense also guaranteed, right? Even if the blazar contribution exists, if this does happen, you would be witnessing a tension between the two things because, of course, the two things, they have to be compatible somehow. And one of the two sides will probably have to give up because, it can be both, but it can also be this. It's tricky.
Yes. Okay. So, but the understanding is that you can explain this very high energy part of the diffuse gamma ray flux without relying on models for the sources. So how to say, you build a model for the population of sources and not for the individual sources and the physics regarding the sources. And you can still explain it. Okay. Thanks. And one more question again about this. So maybe two questions. What is the luminosity that you inject into cosmic rays per cluster for every given cluster? And does this relate somehow to the properties of the cluster? And in that case, so are you also claiming that the clusters are sources of the cosmic rays at energies of 1 eV, or are you well below the observed flux at this value?
Okay, so the typical energy there, if I'm not mistaken, I think it's order 10 to the 40, 37 ergs per second for the luminosity, maybe. Give or take 3 orders of magnitude. Okay, yeah, because this varies, and this varies proportionally to the cluster mass as well.
The mass.
So yes, and we consider the fold distribution because this we consider individual clusters a sample coming from cosmological simulations, so that we can have a sample of all masses as well. And the second part is the
second part was whether or not your calculations for the clusters now, what's the predicted cosmic ray flux in your calculations from these clusters of galaxies?
Yeah, so the point is that the cosmic rays at these energies, they don't necessarily escape the cluster. They just produce things and they remain trapped, or they scatter in another, if they leave the cluster, they go in another direction. So we cannot use the cosmic ray information. On the other hand, this brings in an interesting element, which is our own cluster, right? There might be a background like this within our own cluster.
Right, I see what you mean. If you are in this calorimetric limit, I suppose that everything is confined, or the cosmic rays are losing their energy within this cluster.
Yeah, but with what we know from gas distributions in clusters, at least that's what we get from simulations, and it matches observations, roughly speaking. So that should be the case also for our cluster.
Okay, thank you very much. I have many questions, but I will ask, there is one in the chat. Are there any, by Stavros Papagelos, are there any current or future projects based on smartphone, mobile phone sensors for high energy cosmic rays? Thanks in advance.
Yeah, there is a project. It's called, I forgot the name, but there is a project. I think that there is a Polish group working a lot. Credo, it's the name of the project. They have the idea of using like the CCD camera. So I think it's the CCD in our phones, you know, because it just sparkles every time there is a muon passing by. And if you have the app, this information can go to your phone and you can connect it worldwide. It's a very neat idea, I think. I don't know how well it can be done and what backgrounds or other things that might be going on, you know, if you just turn on your microwave nearby or whatever. I don't know what happens. I have no idea. But it's a very interesting idea.
So Credo, okay.
Credo, yeah.
Thanks again, Stavros. Other questions? Okay, I will ask one more then. So you talked about this contribution to the diffuse background from clusters based on the interactions of the escaping cosmic rays from their sources, I suppose, in the cluster. So have you also considered, because these cosmic rays are produced in some sources and then they escape, and you treat the propagation from this point onward. So have you considered what is the contribution of the individual closed sources in the cluster to these backgrounds?
No.
In other words, what would be, since you know what is the escaping luminosity from galaxies in that cluster, I suppose that each galaxy in the cluster can produce cosmic rays or accelerates cosmic rays within their environment. So what would be the contribution to neutrinos and gamma rays from that?
Yeah, there is, okay. There are two scenarios here. One scenario is one in which you assume that the cosmic ray spectrum inside the cluster is defined by like shocks that are taking place. They're kind of accelerated there. And the second one, you have these embedded sources, like you were proposing. Both scenarios, they lead to not exactly the same, it's different, but compatible signatures. In terms of order of magnitude, I think the slope changes a little bit in this, if you just do these two types of simulations. I haven't checked individual just one source there, but if you just put randomly like 100 sources spread around the cluster, the two scenarios, they tend to be close enough for many sources. If you have just a few sources, things are different.
Okay. Okay, that's interesting. I have to think about that. Other questions? David says, excellent talk. Thank you in the chat. Okay, if there are no other questions, I think that we can stop here. I will stop recording. Thank you very much again, Rafael, for this very nice talk.